So here is something worth thinking about as you settle in tonight. A number. Just one number, and everything follows from it. 280 million cubic yards of concrete. That is how much went into building the Three Gorges Dam in China, the single largest hydroelectric structure ever constructed by human beings. And here is the thing about concrete that makes this number terrifying. Concrete generates heat when it cures. It is a simple chemical reaction. Water meets cement, and the temperature starts climbing. In a small bucket, you would barely notice. The bucket might feel a little warm to the touch. But if you poured all 280 million cubic yards at once and let it cure as a single block, do you know how long it would take to cool down? 125 years. More than a century just to stop being hot. And during all that time, the outer layers would cool faster than the core, shrinking and cracking inward, tearing the structure apart from the inside. The dam would destroy itself before it ever held back a single drop of water. Now here is where the story gets interesting. This problem had already been solved. 70 years before the Three Gorges out in Nevada, an engineer named Frank Crow, his colleagues called him Hurry Up Crow, figured out that you could run ice-cold water through 1-inch pipes embedded inside each concrete block. The cold accelerated the curing, prevented the cracking. Brilliant and simple. So when the Chinese engineers came along, they could just do the same thing, right? Just take Crow's method and scale it up. Do what worked before, only bigger. But only bigger might be the most dangerous phrase in the history of engineering. Because when those Chinese engineers took on a dam that contained 5 times the concrete of the Hoover, they discovered that Crow's cold water pipes were only a small part of the answer. They had to cool every single ingredient before it even went into the mixer. They had to build an entire network of high-speed conveyors to deliver fresh concrete to the worksite within 15 minutes, before it started setting and heating up. They had to spray water mist over the entire construction zone to counteract the brutal Chinese summer. 30,000 workers, pouring an average of 20,000 cubic yards a day, every day, for 8 years straight. At the scale of the Three Gorges, the old solution stopped being a solution. It became just a starting point, one small step into an entirely new set of problems that simply did not exist at the scale of the Hoover. And that is what tonight is about. We are going to take our time with it, starting from the very beginning. Why does doubling the size of something not just double the difficulty, but transform it entirely, turning a familiar problem into something no one has ever faced before? Where is the invisible line between an ambitious project and an impossible one? And why do the most catastrophic failures in engineering history happen precisely when someone says, "Let's just do what we did before, only bigger"? And those are not abstract questions. They are intensely practical. Because here is the part that makes all of this personal. Every building you have ever walked into exists because someone figured out where that line is. Every bridge you have ever crossed, every plane you have ever boarded, every tunnel you have ever driven through. Someone, somewhere, had to take a design that worked at one size and figure out what breaks when you make it 10 times larger.
And right now, as you lie here, listening to this, engineers on the other side of the world are pushing past that line again, building things that would have been unthinkable 20 years ago. And the world you wake up to tomorrow will be shaped by whether they got it right. The answers are buried in thousands of years of human construction, from the pyramids of Giza to the undersea tunnels of the South China Sea. And at every single turn, engineers have discovered the same thing. Scale is not multiplication. Scale is transformation. We are going to meet pharaohs and cathedral builders who pushed stone until it cracked. We are going to watch a French diplomat, celebrated as one of the greatest men of his century, ruined by a jungle he did not understand. We are going to stand inside a wind tunnel with the model of the Eiffel Tower and see why its shape is a mathematical poem. We are going to ride a 16,000-ton ship, lift up the side of the world's largest dam.
And along the way, we are going to discover why a marshmallow in a vacuum jar, a beer barrel manufacturer, and a 270-year-old navigation instrument are all essential parts of the same story. So settle in. Get comfortable. This is a long story, and there is no rush at all. If you drift off somewhere along the way, that is perfectly fine. The structures we are going to talk about have been standing for thousands of years. They will still be here in the morning. Let us start with the oldest ambition that builders have ever had: to build something tall. Very tall. So tall that everyone around you goes quiet and tips their head back. There is something about height that speaks to us at a level deeper than reason. Tall structures declare power, permanence, and mastery over the forces that hold everything else to the ground. And the desire to build tall is as old as civilization itself. Around 2,500 years before the Common Era, on the edge of Cairo, on the Giza plateau, the Egyptians built the Great Pyramid of Khufu. Think about these numbers for a moment. 480 feet tall, roughly the height of a 50-story building. The angle of its faces, 51 degrees, which is steep, uncomfortably steep if you tried to climb it. 2.3 million stone blocks, each weighing about 2.5 tons on average. And here is the part that really stops you. This structure remained the tallest thing human beings had ever built for nearly 4,000 years. 4 millennia. Not the Greeks, not the Romans, not the medieval Europeans. No civilization that came after the Egyptians managed to build anything taller. Not until the Gothic cathedrals of Europe. Let that sit for a second. 4,000 years. The entire Roman Empire, all of Byzantium, the Islamic Golden Age, the whole of the European Middle Ages. And nobody surpassed the height that the Egyptians achieved with stone blocks and human muscle. How did they do it? What tools did they have? What theories did they know? Physicist Richard Tyre traveled to Giza to find out. Standing at the base of the Great Pyramid with Egyptologist Pierre Tallet, he learns something that reshapes the popular image of pyramid construction entirely. Tallet explains, "These are the 3 pyramids of Giza, the most famous in the world. In chronological order, Khufu, the farthest and tallest, then Khafre, then the smallest, Menkaure, all built around 2500 BC. When you look at the pyramids lined up, one detail jumps out immediately. Their slopes are parallel. Every pyramid on the plateau has the same angle of incline, and that, obviously, is no accident. Historian of science Evelyn Barber explains that, thanks to the Rhind mathematical papyrus, we know the Egyptians had the concept of proportionality. They used a small triangle, geometrically similar to the triangle formed by a pyramid's face. That small triangle told the builders exactly where to place the next stone. The small triangle and the pyramid were what we would now call similar figures, and this similarity was reproduced across every pyramid on the plateau. What this means is that the Egyptians had solved the most fundamental problem in large-scale construction, the problem of coordination across space and time. A pyramid is built from the bottom up, layer by layer, over decades. Thousands of workers spread across a vast site have to place millions of blocks in a precise pattern. If even a small percentage of them place their blocks at the wrong angle, the pyramid will not converge to a point at the top. It will arrive at a crooked, uneven mess. The small triangle solved this. Every worker,
anywhere on the pyramid, could check his angle against the same reference. It was, in effect, the world's first building code, expressed not in words, but in geometry. As for the workforce, forget the Hollywood images of whip-cracking overseers and armies of slaves. Pierre Tallet is emphatic about this. The more documents archaeologists find, the clearer it becomes that the work was remarkably well organized by the Egyptian monarchy. The workers were skilled craftsmen, chosen by the king for their abilities. They were well fed, well paid, and employed on a permanent basis. Tallet puts it bluntly. It was something that was absolutely superbly organized by the Egyptian monarchy. We have proof that the workers were professionals, very well fed and very well organized on a permanent basis. American archaeologist Mark Lehner calculated that a team of roughly 5,000 workers laboring over the 27 years of Khufu's reign could have produced the entire pyramid. 350 blocks a day. Methodical, precise, sustained over decades. And what Lehner's work makes clear is that the pyramids were not monuments to brute force. They were monuments to organization, to the ability to coordinate thousands of people over decades toward a single mathematical shape. The Egyptians did not overpower nature. They out-organized it. The pyramids dominated the skyline of the planet until a different kind of ambition appeared in Europe. Not the ambition of pharaohs, but of bishops. Around the year 1000, as Christianity expanded across Europe, a building boom began. The Romanesque style gave way to the Gothic, and Gothic architects made a discovery that changed everything: the pointed arch. Unlike the Roman semicircular arch, a pointed arch directs the load more vertically, closer to the foundation. It allows you to build higher with the same amount of stone. And then there were the flying buttresses, external supports that catch the sideways thrust of the walls and channel it downward, freeing the walls to become thinner and the windows to become enormous. In less than 2 centuries, more than 80 cathedrals were built in France alone, and each one pushed a little higher than the last. It was a genuine race. Researchers at Columbia University, Stephen Murray and Rory O'Neill, built a digital database called Mapping Gothic, which catalogues every Gothic cathedral by vault height and construction start date. When you look at the graph, you see that before the 12th century, heights barely changed. Then, a sharp upward spike. Notre Dame de Paris became the first cathedral in Northern Europe to break through 100 feet.
Amiens pushed higher still, around 139 feet. And then came Beauvais, 1225. But before we get to Beauvais, we need to understand something crucial. What tools did medieval builders actually have? What theoretical framework were they working with? Richard Thayer asks this question standing inside Notre Dame de Paris, under a vault that rises 139 feet above the floor, the equivalent of a 14-story building made entirely of stone. The medievalist and engineer he is speaking with gives an answer that is both humbling and astonishing. In terms of theoretical tools, the builders had almost nothing. Mastery of the compass, the set square, the ruler, very good drafting methods, and the right materials in the right place, entirely empirically, very empirically. They would simply weigh a stone. If it was dense, it went at the bottom. If it was lighter, it went near the top. And here is what is remarkable. When modern engineers run sophisticated calculations on these structures, they discover that medieval cathedrals are enormously over-engineered by today's standards. The pillars of Notre Dame can bear 20 to 30 times the load they actually carry. The builders could not calculate precisely, so they compensated for their ignorance with a massive margin of safety. Make the column thicker than it needs to be. Make the wall heavier than necessary. And that worked. beautifully. Richard Thayer tries one of the medieval tools himself, a rope with 13 knots. You measure one side at 3 units, another at 4, and the third at 5, and you get a triangle with a right angle. The builders did not know the Pythagorean theorem in any formal sense, but they knew this practical rule. And with this rope, this knotted rope, they checked the horizontality of surfaces and the verticality of columns. Thayer tests the horizontal of a structural element in Notre Dame. 800 years after construction, still perfectly level. Rory O'Neill at Columbia adds something that should give every modern engineer pause. Even today, seismic engineers study medieval masonry structures because their computer simulations are not as accurate as the buildings themselves. The real structures perform better than the models predict. Builders who had no theory at all, working purely by intuition, created constructions that we still cannot fully simulate with modern software. Which raises an uncomfortable question. If medieval builders, with a rope and a sense of proportion, created structures more resilient than our computers can model, what exactly have we gained with our theory? And the answer, of course, is not that theory is useless. The answer is that experience and intuition, accumulated over generations and passed from master to apprentice, encoded a kind of knowledge that formal equations still struggle to capture. Murray at Columbia adds context to the building boom. These were not reckless projects. The bishops and their master builders had access to enormous revenues, from agricultural production, from wool and wine trade, from the growing urban economies of medieval France. The cathedrals were, in effect, the megaprojects of their era, funded by the GDP of prosperous regions. Technology was possible because money was available, which is another way of saying the ambition ran as high as the budgets allowed. So, simple tools, empirical knowledge, enormous safety margins. A formula that worked flawlessly, until someone decided to remove part of that margin, to build thinner, lighter, and above all, higher than anyone had ever gone. That is exactly what happened at Beauvais. The Bishop of Beauvais, who began rebuilding the cathedral in 1225, wanted it to be the tallest and most magnificent church in all of Christendom. The vault was to rise to 159 feet, 6 stories higher than Amiens, higher than anything ever attempted. At that point, no one on Earth had built a stone vault that high. The cathedral took 50 years to construct. The builders used the most advanced technology of their era, including iron tie rods and braces binding the arches together. This was reinforcement that earlier cathedrals had not needed. They knew they were working at the limit, and they tried to give themselves extra insurance. In 1270, the choir was completed. The tallest stone vault in the world stood. It stood for 14 years. In 1284, several of the external flying buttresses failed. Parts of the vaulting collapsed. The cathedral did not fall entirely, but the damage was so severe that during reconstruction, an additional column had to be inserted into every single bay, effectively splitting each arch in 2. Jean-Luc, the heritage officer who watches over Beauvais today, shows these columns, cruciform in cross-section, reinforced in every direction. More stable, less vulnerable to wind, and iron tie rods crossing in every direction to hold the structure together against any movement. And the nave, the main body of the cathedral, was never built. Beauvais remains unfinished to this day. If you visit, you enter through a temporary wall where the nave should begin. Beyond that wall, there is nothing. Just an open courtyard where the greatest Gothic cathedral in history was supposed to stand. the tallest vault in the world, and an empty space where the heart of the church should have been. The story does not end there either. In 1573, nearly 300 years after the original collapse, the builders of Beauvais attempted to add a crossing tower to the cathedral, reaching an astonishing 500 feet into the sky. It stood for 4 years. Then, on Ascension Day in 1573, the tower collapsed into the nave. The cathedral was permanently abandoned as a construction project. It stands today as both a masterpiece and a monument to the consequences of pushing past the scale that your materials and your knowledge can support. Murray at Columbia explains why the race happened at that particular moment. It was not just about technology. It was a period when the clergy and bishops were receiving enormous revenues from agricultural production, industrial activity, and trade. The technology was possible because they had the resources to fund it. Which is another way of saying ambition ran ahead of understanding, and the money was there to let it.
O'Neill built a digital simulation, a kind of scientific construction game where you can build Gothic structures in real time and watch them behave. Each block acts as it would in reality, pressing down and pushing outward, reacting to load, deforming under weight. He invites Tailleur to try. The lesson becomes physical, immediate. Every additional foot of height does not just add more weight pressing down. It adds more sideways thrust trying to push the walls apart. And the higher you go, the longer the lever arm of that thrust. The pointed arch helps. It directs the load closer to vertical. The flying buttresses help. They absorb the sideways force. But at a certain height, all of these tricks run out of room. Tailleur tries building in the simulation. "I don't want to brag, but mine is holding," he says. A moment later, "Okay, I spoke too quickly. It didn't last very long." And here is the key lesson. The builders of Beauvais were not fools.
They used the best available technology. They knew they were pushing limits. They added iron reinforcement that earlier cathedrals had never needed. And they still crossed the line. Because each additional foot of height did not just create quantitatively more stress, it qualitatively changed the distribution of forces in the structure. Problems that did not exist at 139 feet became lethal at 159. And no amount of empirical experience building lower cathedrals could have warned them about that. Stone had reached its ceiling. After Beauvais, no medieval cathedral attempted that height again. The graph in Mapping Gothic flatlines after 1225. The tallest cathedral towers in the world, Ulm and Cologne, both in Germany, would only be completed in the 19th century, and their record heights belong to bell towers, not vaults. The vault of Beauvais remains unsurpassed. It would take 600 more years for a new material to arrive that could break through the barrier that stone had set. And when that material came, it changed absolutely everything. In the late 1700s and early 1800s, something sweeps across Europe and America that transforms the built world forever. The Industrial Revolution. Steam engines, factories, railways. The pace of life accelerates in a single generation. And riding that acceleration comes a new building material. Iron. To understand why iron matters so much, you need to understand what was wrong with stone. Stone is excellent in compression. It can bear enormous weight pressing down on it from above. That is why the arch dominated bridge construction for thousands of years. An arch transfers its load as compression, curving downward through the stones
to the supports at each end. But stone is terrible in tension. If you try to pull it apart sideways, it cracks and breaks.
This meant a hard limit. A stone arch could not be too shallow, because a shallow arch starts working in tension instead of compression, and it fails. Iron is a different animal entirely. It is roughly 60 times more resistant to loads than stone, and crucially, it handles both compression and tension. For engineers, this was liberation from the tyranny of the arch. For the first time in thousands of years, they could design structures with entirely new shapes, straight, triangular, anything they wanted. The explosive growth of railways became the catalyst. Trains needed to cross rivers and gorges, and they needed bridges. Lots of bridges, fast, all across Europe and America. Engineers began building in iron at a feverish pace, experimenting as they went, sometimes successfully, sometimes not. And this is where one figure enters the story, without whom nothing that follows makes sense. Gustave Eiffel. Eiffel is not a tower, or rather, not just a tower.
Before his name became synonymous with Paris, he built roughly 100 metal structures around the world. Bridges, railway stations, observatories, and one of the most impressive still stands in the heart of the French Massif Central, the Garabit Viaduct. 1,850 feet long, 400 feet above the Tuyère River, a single main arch spanning 540 feet, a world record at the time. When construction began in 1880, there was absolutely nothing in this location. No roads, no housing. They had to build new roads just to reach the site, then construct accommodation for the workers. Why build a bridge in the middle of nowhere? So the train could get through. Railways were branching across France, but the Cantal department had no direct line linking Paris to the south without skirting around the Massif Central. Mountains stood in the way. The railway had to cross this gorge, deep, wide, with a fast river at the bottom. The problem Eiffel faced was stark. Span 540 feet at a height of 400 feet, with a deep, fast-flowing river below that made it impossible to put support piers in the water. The only option was an arch anchored into the sides of the gorge. But a classical stone arch at that span would collapse under its own weight. Professor Luc Bisbee explains why, using a piece of card between two stones. Curved into a steep arch, the card carries a load. Compression flows downward through the curve to the supports. But increase the span, and the arch flattens out. Tension starts taking over. The card bends and breaks. A solid metal arch could resist tension, but it would be enormously heavy. Too heavy for a gorge this size. Eiffel found the answer. Instead of a solid arch, he built a lattice structure, a truss, a network of hundreds of triangles connected to one another. And this is why the triangle matters so much in engineering. Bisbee compares two shapes, a square and a triangle. Push down on the square, it deforms and collapses because it has no inherent rigidity. Push down on the triangle, it stays stable. The two side elements go into compression, the bottom element goes into tension, and equilibrium is created at the point of load. By building an arch from hundreds of these triangles, Eiffel created a structure that was simultaneously light and extraordinarily strong. Luc Bisbee, clinging halfway up the arch, which he describes as definitely reconsidering my shoe choice for today, says, "I am hanging at the midpoint of Eiffel's magnificent arch structure, and I have to say, it is a real privilege to be able to do this." The secret of Eiffel's success was to harness the strength of another simple shape, the triangle, within a network of open trusses. By making use of a simple system of triangles, Eiffel was able to create a structure that was both light and very strong and stable,
and had a bigger span than ever before. It is a real marvel of engineering, simply genius. Construction took 4 years. Half the structure was pre-assembled in workshops near Paris. The other half was hot riveted together on site in the gorge. Rivets, small iron shafts, heated to red or white hot, inserted into assembly holes, then hammered flat on both sides. As a rivet cools, it contracts, pulling the two pieces of metal together with tremendous clamping force. The arch was built using a technique called cantilevering, constructing from both sides simultaneously, using the existing pylons as support points. Cables anchored to the tops of the pylons held each half of the arch as it grew outward into the void.
The two halves inched toward each other over months, each one a massive iron arm reaching across the gorge, held in place only by the tension in the cables above. When they finally met in the center, high above the river, in the open air, the precision of the junction had to be exact. A gap of even a few inches would have meant months of rework. Eiffel's engineers achieved it perfectly. The viaduct was completed in 1884. Trains began crossing the gorge that same year. And the structure that had seemed impossible a few years earlier became part of the daily routine. Passengers reading newspapers and drinking coffee, while the train carried them across 540 feet of empty air. 400 feet above a river they could not even see from the windows. And it was precisely at that moment, at the peak of this project, that Eiffel's next idea took shape. An even more audacious one. A 1,000-foot tower. The idea did not actually come from Eiffel himself. In 1884, two of his best engineers, Émile Nouguier and Maurice Coquelin, sketched the first drawings of a metal pylon that could serve as a monument for the upcoming World's Fair in Paris. At first, Eiffel was unimpressed. The tower they designed would be inaccessible to visitors, and he did not find it attractive. But when in-house architect Stephen Sauvestre added decorative arches and public platforms to the design, and when the Parisian authorities announced a competition for exactly this kind of monument, Eiffel got excited. 1,000 feet. At the time, the tallest human-built structure on Earth was the Washington Monument, 555 feet, a stone obelisk whose construction had taken decades because the ground beneath it kept sinking. Eiffel was proposing to go almost twice as high, and in metal, not stone. The material choice was wrought iron,
Not cast iron, too brittle, poor in tension. Not steel, too expensive, and not widely available in the 1880s. Wrought iron was produced in a furnace that filtered out carbon impurities. It was not as strong as steel, but it was a highly reliable material with high compressive and tensile strength. Tough, flexible, affordable, and readily available. Eiffel had spent decades building bridges from it and knew its properties intimately. And here is where the scale trap springs. Eiffel knew how to build horizontal structures from wrought iron, bridges, viaducts. But a 1,000-foot vertical tower was an entirely different kind of problem. And at that scale, problems appeared that simply did not exist in bridge construction. The first, wind. A bridge is horizontal. Wind pushes on it from the side, but the bridge's length distributes the force. A tower is vertical. Wind pushes on it at every level, and the speed of the wind increases with height. At ground level, a gentle breeze. At 1,000 feet, a gale. And the wind direction at different heights can be completely different. In the 1880s, these forces were poorly understood. Eiffel and his engineers could only calculate. They had no experimental wind data for a structure this tall. 23 years after the tower's completion, Eiffel would build a wind tunnel in Paris, precisely to study the forces he had only been able to estimate on paper. And today, physicist Benoit Romo uses that very wind tunnel to compare two models, a straight tower and the Eiffel Tower. At a wind speed of 10 miles per hour, the straight tower bends significantly more. The Eiffel Tower barely moves. Same height, same quantity of material, and completely different behavior. Why? Because the shape of the Eiffel Tower, its curved legs, its tapered profile, directs the combined force of wind and the tower's own weight straight downward, following the curves of the structure.
No element experiences sideways bending. Romo says, "This is the best shape imaginable for wind resistance. It has the elegance of a mathematical solution. It is truly optimal." During the Great Storm of 1999, a record wind speed of 84 miles per hour was measured at the top. The tower stood firm. The second problem, foundations. The construction site sat on the bank of the Seine. The soil was saturated with water. How do you build the foundation for the world's tallest structure on potentially unstable, waterlogged ground? Eiffel reached back to his very first major project, a railway bridge across the Garonne River in Bordeaux, built in 1860. As a young engineer, he had faced the same challenge: how to build a support pier 80 feet underwater. He used a technique he had learned from his first employer. Large cast-iron tubes, about 12 feet in diameter, sunk into the riverbed.
The lower chamber was pressurized with compressed air, keeping the water out so workers could excavate on a dry bed. Rubble and mud came up through a central shaft. This innovative technique ensured fast completion of the foundations. Eiffel applied the same method to the tower. In the winter of 1887, around 50 workers began digging the foundations for the north and west pillars, the ones closest to the Seine. Watertight metal caissons protected the excavation from flooding, and then came the third problem of scale, the ghost problem that no one saw coming. Workers in the pressurized caissons began reporting tingling sensations, bleeding, difficulty breathing, and partial paralysis. No one understood what was happening. Today we know it as caisson disease or decompression sickness. When you move too quickly from a high-pressure environment to normal pressure, nitrogen bubbles form in the blood. But in 1887, no one knew this. The government grew concerned. The Minister of Commerce and Industry personally descended into the caisson and came back up alive. This was taken as proof that the work was safe. Construction continued. Then came the assembly, and this is where the scale of the project becomes visceral. 18,038 individual pieces, every single one designed in the workshops at Levallois-Perret, just outside Paris, with tolerances measured in fractions of a millimeter. Each piece arrived at the Champ de Mars on horse-drawn carts, already drilled with its rivet holes, already shaped to fit its neighbors. The precision had to be absolute. On a structure this tall, even a small error at the base would compound into a large one at the top. A millimeter of misalignment in the first section could become an inch by the time you reached the summit. The riveting technique that Eiffel's teams would use was itself a masterclass in organized labor. Each team consisted of 4 men.
One heated the rivet to cherry red in a portable forge. A second held the hot rivet in place with tongs, while a third positioned the bucking bar against one end. The fourth swung the hammer, shaping the other end of the rivet into a dome. As the rivet cooled, and iron contracts significantly as it cools, it pulled the 2 plates together with enormous clamping force. The joint became stronger than the surrounding metal.
These four-man crews worked 12-hour shifts at increasing heights, exposed to wind and cold, balancing on open framework with no safety nets. And the technique they used had been perfected on another famous project, the Statue of Liberty. Ranger Matt Hoss leads a tour inside the statue. What is most impressive about the interior of the Statue of Liberty is how all of this iron and steel works together to hold her over 300 feet above New York Harbor, over 100 years of wind and rain. And she still stands because of this interior structure.
Hundreds of copper plates, her skin, joined by thousands of copper rivets. Steel bars connecting the skin to the iron pylons inside. Light, strong, and tall. The experience Eiffel gained here proved crucial for the tower. On March 31st, 1889, Eiffel raised the French flag at the top of his tower, 1,024 feet above the ground, the tallest structure in the world. Built in less than 2 years. But iron had its limits, and scale was preparing its next blow. In the 1880s, around the very same time Eiffel was completing his tower, roughly 200 iron bridges collapsed in the United States. Engineers poorly understood how cast iron behaved under the repeated, cyclical loads of passing trains. Bridges that looked solid on opening day crumbled after a few years of service. The age of iron was ending. In its place came steel, an alloy of iron and carbon, far stronger, more predictable, and, critically, weldable.
From the early 20th century, steel would completely transform engineering because, unlike iron, it could be welded, and that totally transformed assembly technology. Steel would open a new chapter in the history of bridge building, a chapter where spans are measured in miles, where decks hang from cables thinner than a human torso, and where scale would once again expose problems that nobody expected. Problems involving an invisible force that had, until then, been treated as a nuisance rather than a mortal threat. Wind. The history of bridge building is really the history of a single problem that keeps reformulating itself at a larger scale with each passing generation. How do you carry a load across empty space? The Romans solved it with stone arches, maximum span about 115 feet. Beyond that, the sheer weight of stone crushed the arch from within.
Eiffel stretched the limit to 540 feet by replacing solid stone with an open lattice of wrought iron triangles. But by the end of the 19th century, engineers were reaching for spans of thousands of feet. And to get there, they had to invent entirely new kinds of bridges and pay prices that no one anticipated. One of the most dramatic breakthroughs is the Brooklyn Bridge in New York. Its story is the story of a single family that paid for the ambition of scale with 3 generations of sacrifice. The bridge was designed by John Roebling, a German-born engineer. 5,989 feet across. At the time construction began in 1870, it would be the longest bridge in the world. A suspension bridge, the roadway hangs from steel cables draped over 2 massive stone towers and anchored into the bedrock on each shore. The load travels up the cables, into the towers, and down to the foundations. An elegant idea,
and one that allowed spans far greater than any arch. But Roebling never saw his bridge built. While surveying the site on the south side of the Brooklyn Tower, he did not notice an incoming ferry. The ferry crushed his foot. Roebling refused conventional medical treatment and insisted on pouring water over the wound. He died of tetanus. Command passed to his son, Washington Roebling. And here is where scale delivered its next blow. To build the two great towers in the bed of the East River, engineers sank enormous wooden caissons, watertight chambers roughly 164 feet long and 98 feet wide. Blocks of granite for the towers were stacked on top, gradually pressing the caissons down into the riverbed. At a depth of about 100 feet, in a cramped, damp, pressurized space, the air pressure was 3 times higher than at the surface. Laborers spent months digging by hand, excavating mud and rock to anchor the foundations in solid bedrock. And the workers began to fall ill. Strange, terrifying symptoms. Joint pain so severe that men could not walk, partial paralysis, bleeding from the nose and ears. Some workers died. The condition seemed random, striking some men and sparing others, with no obvious pattern. Doctors called it caisson disease or the bends, but they had no idea what caused it and no effective treatment. The same affliction that would later strike Eiffel's foundation workers in Paris, but here, at 100 feet down, where the air pressure was 3 times higher than at the surface, the consequences were far more severe. Men who had been healthy in the morning were carried out on stretchers by afternoon. Washington Roebling went down into the caissons himself. He wanted to be part of the team, to work alongside his men. And he paid for it. He contracted caisson disease so severely that he spent the rest of the construction bedridden, watching the bridge through a telescope from his bedroom window.
And then his wife stepped in. Emily Warren Roebling became the conduit between her husband and the construction site, carrying his instructions to the workers, carrying information from the site back to him. Photographer and bridge historian Dave Frieder puts it simply. I think without Emily Roebling, you wouldn't have the Brooklyn Bridge today. She was one of the first women civil engineers that really helped. What she did was absolutely incredible. The bridge opened in 1883 to enormous public celebration. Its steel cables, 4 main cables, each nearly 16 inches in diameter, consisting of thousands of individual steel wires bundled together, carry the roadway, transferring the load upward through the cables, over the towers, and down into the bedrock on each shore. The suspension design made it possible to span a distance that would have been unthinkable for an arch bridge. The Brooklyn Bridge stood as the longest suspension bridge in the world for more than 20 years. And the story of the Roebling family, the father who died before construction began, the son who was crippled by the technology he was pioneering, the wife who stepped in and became one of the first female engineers in American history, became one of the most celebrated narratives in the history of civil engineering. Dave Frieder, who has spent years documenting the bridge photographically, walks across it at dawn. Every time I walk on this bridge, I think about what the Roeblings sacrificed. Washington spent years watching through a telescope. Emily spent years carrying his vision to the workers, and the bridge stands. But suspension bridges, for all their elegance, carried a hidden vulnerability. The longer and lighter they became, the more they were exposed to a force that earlier, heavier bridges had simply shrugged off.
And that force, wind,
would demand an entirely new kind of thinking. In the 1950s, British civil engineer Sir Gilbert Roberts was tasked with designing the longest windproof bridge on Earth, a crossing over the River Severn between England and South Wales. The main section would stretch 5,243 feet, roughly a mile. The location was brutal. The River Severn lies inland from the Atlantic Ocean. The high ground on the south shore and the Welsh mountains to the north create a natural funnel for the prevailing southwesterly winds, increasing their power. Building a bridge that could withstand those winds was absolutely essential. Professor Luke Bisbee stands underneath the Severn Bridge, 143 feet above the water. Even on a relatively calm day,
Standing here underneath the bridge, you really get a sense of the wind that they were up against.
When Roberts and his team tested their original design in a wind tunnel, a conventional truss box girder deck, the model broke. While they waited for a replacement, engineers began experimenting with other shapes, and someone noticed something about airplane wings. A wing has a curved surface on top and a flat surface on the bottom. Air passing over the curved top has to travel farther, so it speeds up. According to Bernoulli's principle, faster moving air exerts lower pressure. The high pressure below the wing pushes upward toward the low pressure area above, and that is lift. That is how airplanes fly. The engineers at the Severn Bridge turned this principle upside down, literally. They designed a bridge deck shaped like an inverted wing, the curved surface on the bottom instead of the top. Now the air speeds up underneath the deck, the pressure drops below, and the higher pressure above pushes the deck down. The stronger the wind blows, the harder the bridge is pressed onto its supports. Bisbee demonstrates with a model airplane on a scale. Right side up, the weight decreases as lift pulls the plane upward. Upside down, the weight increases as the inverted wing pushes it onto the scale. And of course, this is exactly the principle that the engineers used on the Severn Bridge. Sir Gilbert Roberts and his team created an aerodynamic steel box girder deck, the first of its kind in the world. Hollow, only about 10 feet deep, with a cantilevered footway on each side. The resulting deck was far lighter and far more aerodynamically stable than any bridge deck previously built. It did not fight the wind. It used the wind to hold itself down. During the bridge's history, 13 vehicles crossing it have been blown over by storms. Cars have been lifted off the road surface and deposited on the opposite side. But the bridge itself has never moved. Not once.
More than 300 million vehicles have crossed it since it opened in 1966, through 6 decades of Atlantic weather, and the bridge stands exactly where its builders placed it. An accidental discovery born from a broken wind tunnel model and a moment of creative desperation. And it solved a problem that had haunted bridge engineers for decades, the problem that had destroyed the Tacoma Narrows Bridge in 1940 and shaken confidence in suspension bridge design worldwide. After the Severn, the problem of wind and bridges was, if not fully solved, fundamentally reframed. Wind was no longer an enemy to be resisted. It was a force to be redirected. But the Severn Bridge was roughly a mile long. What happens when you need a bridge that is 1.5 miles long and over 1,100 feet above the ground? The Millau Viaduct, southwest France, the Tarn Valley. The Tarn is a river that has spent millions of years carving a gorge through the limestone plateau of southern France. The valley it has created is about 1,000 feet deep, nearly 1.5 miles wide, and breathtakingly beautiful. And for decades, the medieval town of Millau, perched at the bottom of this gorge, sat directly in the path of the busiest transport link between Paris and the Mediterranean coast. Every summer, a traffic nightmare. 3 hours to crawl through town. Engineer Michel Virlogeux received the task. Bypass the town and carry the road across the enormous Tarn Valley. The first difficult point was to select where to cross the valley, because there is almost 1,000 feet between the plateau and the deep part of the valley. There have been big debates. Many alternatives were analyzed. Finally, it was decided to fly over the valley. The result? A bridge stretching 1.5 miles, towering 1,125 feet above the ground, taller than the Eiffel Tower. 7 slender concrete piers touching the valley floor, a 36,000-ton aerodynamic steel deck held in place by 154 cable stays. a construction deadline of less than 4 years, with fines of up to $30,000 for every day of delay. A designed lifespan of 250 years. Every element of this bridge required solutions that had never existed before. The piers, each one a different height because of the uneven valley floor. The tallest, 804 feet, a world record. Octagonal in cross-section, splitting into a Y shape about 300 feet below the deck to provide flexibility. All 7 piers had to be built simultaneously across 7 separate construction sites.
Engineers used a self-climbing formwork system, a hydraulic-driven mechanism that pushed a giant reinforced concrete mold upward along each pier. Every cycle took 3 days. Pour the concrete in a 13-foot section, wait for it to set, disassemble the mold, push the frame upward on hydraulic jacks, reattach, reassemble the mold, pour the next section. The piers were completed in just over 2 years, a month ahead of schedule. But the real challenge waited above. How do you place a 36,000-ton steel deck on top of those slender, towering piers? Using a crane was impossible at that height. The only option, slide the deck out from both sides of the valley, from plateau to plateau. But pushing steel across the surface of the piers would generate friction. Friction would create lateral force. And lateral force on a tall, thin pier is a recipe for catastrophe. The solution came from an accidental discovery made in a laboratory in 1938.
American chemist Roy Plunkett had been developing non-toxic refrigerants when an experiment with a gas called tetrafluoroethylene went wrong. The gas unexpectedly solidified, coating the inside of the test tube with a waxy resin. Inadvertently, Plunkett had created one of the slipperiest substances known to science. It would eventually be trademarked as Teflon. Engineer Rhys Morgan demonstrates a metal sled loaded with about 100 pounds of bricks on a bare metal sheet requires about 26 pounds of force to move. The same sled on a sheet coated with Teflon starts sliding at just 15 pounds. And with Teflon, the sled can carry 40% more weight at the same effort. How about that? Engineers at Millau created a device called a translator, 2 wedge-shaped blocks coated in Teflon, driven by hydraulic rams. The upper wedge slides up the lower wedge, lifting the deck off each pier and pushing it forward about 2 feet at a time. Then the lower wedge slides back, lowering the deck onto the pier again. All the translators on all the piers moved simultaneously, by the same distance. No lateral force was ever applied to any pier. 15 months of launching. 2 sections of deck, creeping toward each other from opposite sides of the valley, following a gentle curve with a radius of about 12 miles. GPS technology provided pinpoint accuracy. In May 2004, the 2 sections met above the Tarn River. The gap between them measured a few millimeters. Virloge. This system was really the key to success. But a bridge this size also needed cable stays, and the engineering of those stays drew directly on a pioneering innovation from the 1950s. Structural engineer Jonathan Leading explains the principle using his own body. Imagine my arms are cantilevering out from my body, and I'm trying to hold a bucket of water. I need to do a lot of work with my arms. Now I pull a rope over my head, and the weight is transferred through the rope to my head and down to the ground. That is exactly what is happening behind us. The problem with early cable-stayed bridges had been distributing the loads evenly among the cables. Get one cable overtensioned, and the consequences could be disastrous. German engineer Franz Dingler solved this in the 1950s at the Sundsvall Bridge in Sweden, the first true modern cable-stayed bridge. Dingler created mathematical formulas to calculate the precise tension required for each cable, then tensioned them individually on site. An engineering first. At Millau, Dingler's methods were magnified to an unprecedented scale. 6 cable-stayed spans instead of 1. 22 cables per pylon, 7 pylons. The strongest cables, made of 91 steel strands, had a braking strength of 2,000 tons. 28 trucks weighing a combined 900 tons drove across the bridge simultaneously. A convoy of loaded vehicles, bumper to bumper, stretching across the entire deck. The bridge engineers watched their instruments. The deck flexed a few inches under the load, exactly as predicted by the calculations, and held firm. The cables did not sing, did not snap, did not stretch beyond their design parameters. The bridge passed every test. The opening ceremony took place in December 2004, 2 months ahead of schedule. Nearly 5 million vehicles cross it every year. When you have spent years working and fighting for a bridge, and suddenly it is finished, there is really a moment where you don't know what to do. Bridges conquered the void. They learned to resist wind, span miles, and hang from cables thinner than a human body. But what about conquering water itself? Not throwing a bridge over it, but blocking it, taming it, forcing it to work.
And what happens when the concrete you use to hold back a river generates enough heat to destroy itself from within? Let us take a step back and talk about concrete, because concrete is arguably the most important building material in human history. And the story of how it was invented begins on a rock in the middle of the sea. The Eddystone Rock sits in the English Channel, one of the busiest and most dangerous shipping lanes in the world, about 14 miles from the port of Plymouth. For centuries, ships had been wrecking on this rock in fog and storms. As maritime trade grew in the 17th century, the authorities decided there must be a lighthouse. The first lighthouse was a wooden tower built by Henry Winstanley in 1696. About 80 feet tall. It stood for 7 years before a storm obliterated it. Its replacement survived 47 years until it was destroyed by fire. 2 lighthouses, 2 different causes of destruction, but the lesson was the same.
Wood on an exposed rock in open sea could not last. In 1756, the challenge fell to an engineer named John Smeaton. He decided that the sea must give way to the building, not the other way around. He would build his lighthouse from stone. But stone in the ocean is not the same thing as stone on land. The mortar that holds stone blocks together, a traditional mixture of sand, clay, straw, and lime, does not set in water. It just dissolves and washes away. Smeaton experimented with dozens of different formulas and discovered that a specific combination of lime, clay, and iron slag, what he called hydraulic lime, would harden even when submerged. Professor Luke Bisbee recreates Smeaton's experiment on camera. He prepares 2 samples, traditional cob mortar and Smeaton's hydraulic lime mixture. Both are packed into cardboard tubes and placed in water. Half an hour later, the results are dramatic.
First, let's look at the tube filled with the traditional mud mortar. Let's see exactly how much it's set. And you can see absolutely nothing. It's a mess. Then the second tube. This is the one we're much more interested in. This is the one with Smeaton's hydraulic lime technology. I can immediately feel that this one is much more solid. If I squeeze it, nothing happens. If I have a look inside, this is now very, very solid. That combination, setting quickly and setting underwater, completely revolutionized civil engineering. What Smeaton had created was the forerunner of Portland cement. Portland cement is the key ingredient in all modern concrete. Using his hydraulic lime, Smeaton dovetailed together nearly 1,500 blocks of granite into a rock-solid structure that would stand against the full fury of the English Channel. The lighthouse lasted over 120 years.
It was eventually dismantled, not because the structure failed, but because the rock beneath it began to crack. The lower portion was left in place because the Victorians found it too difficult to take apart. The upper portion was relocated to Plymouth Hoe as a monument to Smeaton's genius. Bisbee stands on the Plymouth waterfront. So here we have the original 250-year-old granite blocks, reassembled here with mortar much like the original. Incredible that it still looks so good. And if I look really carefully, way out there on the horizon, I can just see the base of Smeaton's original tower, standing next to the new tower. This was really the game changer in concrete worldwide. Portland cement, the descendant of Smeaton's invention, made it possible to build with concrete on an industrial scale. And in the 20th century, engineers turned that power against the mightiest force in nature, water. The American Southwest in the early 1930s.
A region desperate for both water and electricity. The solution: a dam on the Colorado River, the Hoover Dam. Professor Andrew Smith flies in by helicopter. At the time of its construction, this was the world's largest concrete structure that had ever been built. Even today, roughly 80 years later, it takes your breath away. 700 feet tall, a base thickness of 660 feet, 6.6 million tons of concrete. And here is where we return to the problem we started this evening with. Concrete generates heat when it cures. Smith mixes cement and water on camera, and you can watch the thermometer climb. The fresh mix reads about 111 degrees Fahrenheit. Half an hour later, it peaks at about 154 degrees, an increase of over 40 degrees. And you could really feel the heat. Engineers estimated that if they had poured all 6.6 million tons of concrete in one continuous pour, it would have taken 125 years to cool, with catastrophic cracking all the way through. The dam would have torn itself apart. The solution came from the project's general supervisor, Frank Crowe, nicknamed Hurry Up Crowe, on the construction site. His idea was deceptively simple. Instead of pouring the dam as one continuous mass, break it into a series of gigantic blocks. And inside each block, embed a network of 1-inch pipes carrying ice-cold water, produced by a specially built refrigeration plant. The cold water would draw the heat out of the concrete as it cured, accelerating the process and preventing the deadly temperature differentials. Deep inside the dam, in the old engineers' inspection tunnels, you can still see traces of those pipes today.
Smith runs his hand along the wall. The solution was to pass extremely cold water through 1-inch pipes, and the amazing thing is we can actually still see evidence of those pipes here. In 1931, at the height of the Great Depression, thousands of workers poured into the Nevada desert for what would become one of the most grueling construction jobs in American history. Temperatures on the canyon floor regularly exceeded 120 degrees Fahrenheit in summer. Men worked in shifts around the clock, 3 shifts, 8 hours each, 7 days a week. They poured the dam block by block, continuously cooling the concrete with Crowe's refrigeration system, monitoring temperatures, adjusting flow rates, managing a logistics chain that stretched from the refrigeration plant to the dam face. The job was finished in 1935, 2 years ahead of schedule, a remarkable achievement that owed everything to Crowe's relentless pace and meticulous planning.
And behind the dam, one of the most remarkable bodies of water on Earth appeared. Lake Mead, at the time, the world's largest man-made lake. At full capacity, the volume of water could cover the entire state of Connecticut with 10 feet of water. The Hoover Dam was a triumph, but it was only a prologue. The Three Gorges Dam in China is 5 times larger by volume of concrete, more than 1.5 miles long, 594 feet tall. And the problem of concrete cooling solved by Crow's cold water pipes in the 1930s, became a completely different animal at this scale. Did they use Crow's pipes? Yes, but that was just the beginning. The ingredients of the concrete were air-cooled before they were even mixed. High-speed conveyors brushed the fresh mix from the batching plant to the construction site in 15 minutes, before it could start setting and generating heat.
Workers sprayed water mist over the entire work area to reduce the effects of the brutal summer weather. An average of 20,000 cubic yards of concrete were poured every single day. At the peak, more than 30,000 workers were on site simultaneously. The pour took 8 years. In 2006, the dam was completed. Deputy Director of Construction Technology, Mr. Kiad Ding. It's a most important milestone of the project. Of course, I was very excited at that time. But the scale of 3 gorges created problems that the Hoover never had to face. One of the most dangerous: overflow. When water levels in the reservoir rise too high, the excess must be released. But if that water simply spills over the top of the dam and crashes into the foundations below, the result is something called toe scour. The flowing water erodes the base, undermining the dam's structural integrity, and then the dam collapses.
Rhys Morgan demonstrates on a small model. Water pouring over a miniature dam, hitting the base, eating away at the foundation. The integrity of the dam becomes very questionable, and it starts to collapse. So there it goes. The consequences of the Three Gorges Dam failing are almost beyond imagination. Tens of millions of people live downstream along the Yangtze. The solution to toe scour was pioneered in the 1930s by French engineer André Coyne, who built the Massy Dam on the River Doubs. Morgan stands beside the dam's overflow channel. This is a ski jump spillway. It's called that because it has a lip at the bottom, just like a ski jump. Instead of carrying on all the way to the base of the dam, the water gets flicked into the air, turns into droplets as it mixes with air, and the energy is dissipated. The Director of Engineering Projects at Massy confirms the ski jump spillway is necessary.
Otherwise, the water would overtop the crest, impact the toe, undermine the foundation, and generate the total collapse of the dam. At the Three Gorges, Coyne's innovation was scaled up to 46 ski jump spillways, the largest battery of spillways on any dam in the world. When reservoir levels rise during the rainy season and the gates open, hundreds of thousands of cubic feet of water per second are launched over 300 feet away from the dam's foundations. The water arcs through the air, breaks into droplets, mixes with the atmosphere, and by the time it reaches the riverbed downstream, most of its destructive kinetic energy has been dissipated harmlessly into mist and spray. Mr. Kiad Ding smiles when he describes the effect. The spillway looks like a piano. From above, with all 46 channels discharging simultaneously, the parallel streams of white water do indeed look like the keys of an enormous keyboard, played by the river itself. The sheer volume of water that the Three Gorges spillways can handle is staggering. At maximum discharge, the flow rate through the spillways alone exceeds the average flow of many of the world's major rivers. Managing that volume, deciding when to open which gates, by how much and for how long, requires continuous monitoring and real-time decision-making. Too little discharge and the reservoir overflows. Too much and the downstream communities are flooded. The dam operates in a narrow band between these two catastrophes. Every day, every season, every year. And then there is the matter of navigation. The Yangtze is the third longest river in the world, nearly 4,000 miles. It is the lifeblood for thousands of communities along its banks. Cargo traffic exceeds 100 million tons per year. Completely blocking this vital waterway was simply not an option. For cargo ships, the engineers built the world's largest ship lock, a staircase of concrete chambers, each one large enough to swallow an ocean-going freighter whole. More than a mile long in total, the lock raises and lowering river traffic 371 feet through 5 enormous steps. Each step fills and drains using gravity alone, no pumps. Water flows in from the reservoir above, lifts the ship, and when the level matches the next chamber, the gates open and the ship moves forward. The lock operates 24 hours a day, 7 days a week. The sheer volume of water that moves through the system is staggering. Each lockage, one ship going up or one ship going down, uses tens of millions of gallons. And the water must come from the reservoir, which also supplies drinking water and irrigation to millions of people downstream.
Managing that balance. Enough water for navigation, enough for agriculture, enough for cities, is an ongoing engineering challenge that the builders of the original canal locks in the 19th century never had to consider. At the scale of 3 gorges, water management became as complex as the dam itself. But passing through the 5-step lock takes 3 hours and 40 minutes to 4 hours. For passenger vessels on tight schedules, that is far too slow. So the engineers turned to an idea from Victorian England. In 1870, in the north of England, engineer Edwin Clark built the Anderton boat lift, the world's first operating boat lift, to link the Trent and Mersey Canal with the River Weaver below. 2 watertight tanks, called caissons, filled with water, and the boats floating in them, were balanced on hydraulic rams connected by a pipe.
The genius lay in the simplicity. All you needed to move one tank up and the other down was 5 centimeters of extra water in the upper tank. Its slightly greater weight pushed it down, and the lower tank rose, nearly effortless. And the journey took less than half an hour, instead of the laborious hours required by the old locks. Dr. Rhys Morgan rides the Anderton boat lift himself. It's extraordinary. It's a 3-story high marvel of Victorian engineering. It's just fabulous. The lift is still in operation today, more than 150 years after its construction. The original hydraulic mechanism was replaced by electric motors in the 20th century, but the fundamental principle remains unchanged. 2 balanced tanks, connected by a simple mechanical system, doing the work of a dozen conventional locks in a fraction of the time. The Anderton lift raises boats about 50 feet. That is a manageable height. The engineering is elegant, the forces are modest, and the consequences of failure are limited to a few barges and a muddy canal. Now multiply that by 7. At the 3 gorges, Clark's principle was scaled up beyond recognition. Instead of narrow boats, 3,000-ton passenger liners. Instead of 50 feet, 371 feet of vertical rise. Instead of hydraulics, a system of massive counterweights and pulleys, lifting a steel pool 433 feet long. The counterweight alone weighs nearly 16,000 tons. Engineer Jan Akinola rides the shiplift during testing. It's the weirdest sensation. It feels like I'm in a big, massive swimming pool being pulled up many meters, or in a lift with a massive pool in it being lifted up. It's an engineering feat, a beauty in so many ways. The physics is simple. The pool full of water, with the ship floating in it, weighs almost exactly the same as the counterweight.
The system is in near-perfect balance. The motors only need to overcome friction and the small weight difference, a tiny fraction of the total load. It is the same principle that Edwin Clark used in 1870 at the Anderton boat lift, scaled up by a factor of more than 100. The elegance of the idea is preserved, but the engineering required to implement it at this scale, the steel cables, the counterweight system, the alignment of the guide rails, the seals that prevent water leaking from the pool during the lift, is entirely new.
None of it existed before this project demanded it. When fully operational, the ship lift transports passenger vessels from top to bottom in 30 to 40 minutes, 8 times faster than the lock system. A 3,000-ton ocean liner carried straight up the face of a dam in the time it takes to watch a television episode. The Three Gorges Dam is the clearest illustration of our central theme.
Every single element, the concrete, the spillways, the ship passage, is a proven idea taken from a smaller structure and scaled up to a level where the original principle survives, but the engineering implementation has changed beyond all recognition. Crow's pipes became an entire industrial cooling system. Coyne's single ski jump became 46. Clark's quaint canal lift became a 16,000-ton counterweighted monster carrying ocean liners. And every one of those transformations required engineers to solve problems that the original inventors could not possibly have imagined. Because at the scale of Three Gorges, the old rules still applied, but they were no longer enough. Dams conquered water by holding it back. But what about reshaping the land itself to redirect water, carving a path through an entire continent so ships can pass from one ocean to another?
And what happens when a man who has triumphed at one canal takes on a second in a completely different landscape, with absolute confidence that his experience will see him through? This chapter is perhaps the purest illustration of our central idea. The story of one man who accomplished the impossible, was lifted onto the highest pedestal of fame, and was crushed when he attempted to repeat his triumph at a different scale, in a different landscape, with an unshakable confidence that his experience would carry him through. Let us begin with a small canal, the Corinth Canal in Greece. The idea of cutting a channel through the narrow Corinth Isthmus to connect the Ionian Sea with the Aegean and spare ships a 400-kilometer detour around the Peloponnese is almost 3,000 years old. The ancient Greeks considered it. The Romans drew up plans. But it was not until the end of the 19th century that anyone actually managed to do it.
About 3.5 miles of trench, carved straight through rock. Over 12 million cubic yards of earth excavated. More than 10,000 workers. One of the first major construction projects to use dynamite and nitroglycerin. Though nitroglycerin, as anyone who has handled it can tell you, is profoundly dangerous. They tried it. You can see the results. The Corinth Canal is the simplest type of canal there is, a sea-level canal. You dig a trench between two bodies of water that are at the same elevation, and they fill the channel themselves with salt water. No locks, no artificial lakes, no pumping. Just dig. Now let us talk about the Suez Canal, and let us talk about Ferdinand de Lesseps. De Lesseps was not an engineer. He was a French diplomat, an entrepreneur, a man of enormous charm and even more enormous ambition. In 1859, he began construction of a canal through the Suez Isthmus, 101 miles through the Egyptian desert, connecting Europe with Asia without the treacherous voyage around the Cape of Good Hope. Tens of thousands of Egyptian laborers began the work by hand, pickaxes and shovels. Later, steam-powered dredging machines replaced manual labor, one of the early triumphs of industrialization. On November 17, 1869, the new waterway was ceremonially opened. Empress Eugénie of France sailed through on the imperial yacht. Verdi was commissioned to compose an opera for the occasion, though Aida would not premiere until 2 years later in Cairo. The whole world marveled. A canal through the desert, connecting two seas, eliminating the weeks-long voyage around Africa. For its creator, the completion was a crowning glory beyond anything he could have imagined.
De Lesseps achieved a level of fame that is almost unimaginable by today's standards. He was hailed as one of the greatest Frenchmen alive, He navigated international relations, contributed to the construction of the Statue of Liberty, and was even invited to join the Académie Française, although he was not a writer. His success, according to historians, led to his skills being somewhat overestimated. And this is exactly the point where the story turns. Because de Lesseps became convinced, absolutely unshakably convinced, that he was the best man in the world to build the Panama Canal. And the people around him agreed. His reputation was so enormous, his success at Suez so complete, that questioning his judgment seemed almost absurd.
When he announced the Panama Project at an international congress in Paris in 1879, the audience voted overwhelmingly to proceed, despite the fact that several engineers at the Congress warned that a sea-level canal through the mountains of Panama was physically impossible. De Lesseps overruled them. He had done the impossible once. He would do it again. He had already built one great canal. He understood how it was done. He had the experience, the reputation, and the connections. Panama was just Suez in a different place. Just in a different place. Those 5 words became a death sentence, because Panama was not Suez, not even close. Suez was a flat desert. The terrain was dry, the soil was manageable, the climate was hot but predictable. Panama was a narrow strip of 725 kilometers of land between Latin America and North America, covered in dense, humid tropical jungle. And running right through the middle of the isthmus was a mountainous area called the Culebra, rising over 300 feet above sea level. The French arrived in Panama in 1882 and immediately discovered that they were not in the desert anymore. The geology was completely different. Where Suez had been flat and cooperative, the Culebra was made of crumbly, unstable rock. Every time workers dug into the hillside, the loosened earth triggered landslides. And those landslides, amplified by the torrential tropical rains that hit Panama for months on end, wiped out entire construction sites. Workers would excavate a section, and the rains would fill it back in. They kept having to start again. Historians describe it as a truly Sisyphean task. But the geology was not even the worst problem. The worst problem was invisible, microscopic, and it was killing workers by the thousands. Mosquitoes. The Panama region was infested with mosquitoes, carrying yellow fever and malaria. And in the 1880s, nobody understood the connection. Doctors at the time had no idea that these diseases were transmitted by insects. Their medical practices, in fact, made the situation catastrophically worse. It was believed that placing a basin of water at the foot of a patient's bed would prevent ants from climbing up to the patient. A reasonable idea on its face, except that mosquitoes were laying their eggs in that water. The hospitals were breeding grounds for the very diseases they were trying to fight. Tens of thousands of workers died. The death toll was staggering, relentless, and completely mysterious to the men in charge. Unable to stop the epidemic and watching his workforce shrink by the week, de Lesseps was forced to reconsider everything. The original plan, a sea-level canal dug straight through the mountains, exactly as he had done at Suez, was proving physically impossible. The Culebra cut alone was consuming years of effort and billions of francs, with landslides erasing months of progress overnight. Eventually, de Lesseps agreed to revise his approach. With the engineering support of Gustave Eiffel, yes, the same Eiffel who was simultaneously completing his tower in Paris, he abandoned the sea-level plan and adopted the idea of a canal with locks, better suited to the mountainous terrain. Eiffel designed a series of lock gates that could raise and lower ships through the elevation changes. It was a fundamentally different engineering approach, and it was the right one. But it came far too late. After 7 years, 1 billion francs had been spent with almost nothing to show for it. On February 4th, 1889, the very same year Eiffel completed his tower in Paris,
the Panama Canal Company went bankrupt. 85,000 small investors lost everything. The scandal was enormous. The 88-year-old de Lesseps, once the most celebrated man in France, was found guilty. Only his advanced age spared him a 5-year prison sentence. And then comes the second act. While France nursed its wounds, the United States moved in. Theodore Roosevelt wanted the canal. He saw it as the centerpiece of a future American world empire. The US redeemed the French concession, effectively making the canal zone American territory. And the very first thing Roosevelt's men did was not to start digging. They spent more than a year killing every mosquito in Panama. Because by this time, the early 1900s, it had been scientifically established that yellow fever and malaria were transmitted by mosquitoes.
The discovery had been made by Cuban physician Carlos Finlay and confirmed by US Army surgeon Walter Reed. Armed with this knowledge, Colonel William Gorges led a systematic campaign, draining standing water, spraying oil on puddles, fumigating buildings, screening windows, clearing brush for hundreds of yards around every worksite. The effort was enormous and unglamorous. No one builds monuments to mosquito eradication, but it saved thousands of lives. The Americans understood something that the French had not. Before you can solve an engineering problem, you have to solve the problems that have nothing to do with engineering. Health first, then logistics, then environment. Only then, once the invisible variables have been addressed, can you pick up the shovels and start digging. And the invisible variables are the ones that no amount of canal building experience can prepare you for, because they are specific to the new geography, the new climate, the new biology. They are, by definition, the things you did not encounter last time. Once the mosquitoes were dealt with, the US Army took over construction. Confronted with the same geological nightmares that had defeated the French, the landslides, the crumbling Culebra, the Americans did not try to dig a sea-level canal. Instead, they embraced the lock system that de Lesseps had adopted too late. They dammed the Chagres River, flooding a large part of the isthmus and creating an enormous artificial lake, Lake Gatun, sitting about 85 feet above sea level. Ships would rise to the lake through one set of locks, cross the lake, and descend through another set of locks on the other side. The locks were built to match the scale of the ambition. Gates 82 feet tall, chambers over 1,000 feet long, walls thick enough to contain the tremendous water pressure. An innovative system of locomotive tugs, small electric engines running on rails alongside the lock chambers, stabilized the ships as they passed through, keeping them centered and preventing them from scraping against the concrete walls. The tug system was necessary because the ships, floating in the turbulent water of a filling lock, were difficult to control with their own engines. The Culebra Cut, the section through the mountains that had defeated the French, remained the most dangerous part of the project, even for the Americans. The unstable rock continued to slide, and the excavation had to be widened repeatedly. Geologists estimated that for every cubic yard of rock removed by the workers, nature added half a cubic yard back through landslides. The cut was not fully stabilized until years after the canal opened. On August 15, 1914, after a 30-year construction saga that claimed the lives of 27,000 men, the gates of this new interoceanic highway were finally opened. 48 miles of canal connecting the Pacific and Atlantic Oceans. The voyage from San Francisco to New York, previously about 14,000 miles around South America, was now just under 6,000. While Europe plunged into the First World War, the young American nation seized control of one of the most strategic waterways on Earth. Think about what happened here for a moment. The same canal, the same isthmus, the same goal, and two entirely different outcomes. The French arrived with the confidence of Suez behind them and were destroyed by variables they never anticipated. The Americans arrived with the humility of the French failure in front of them, and they spent their first year not digging at all, just killing mosquitoes.
The difference between catastrophe and triumph was not intelligence, not resources, not technology. It was the willingness to accept that past success might be irrelevant. 90% of global trade today is seaborne. Container ships have grown exponentially since the canal opened in 1914. By the early 2000s, the largest vessels, called post-Panamax ships, could no longer fit through the original locks. The canal was becoming a bottleneck for the global economy. In 2007, Panama, which took over control of the canal zone from the United States in 1999, began construction of a third set of locks to accommodate 21st century shipping. Ilia Marotta, a Panamanian engineer who dedicated 9 years of her life to the project, walks through the new lock chambers and explains the challenge with obvious pride. The new lock chambers are massive, about 180 feet wide and over 1,400 feet long.
You could lay the Eiffel Tower lengthwise inside one. The gates, 16 of them, sliding instead of the traditional swinging type, range from 2,400 to 4,200 tons each. But here is the clever part. Only about 15% of each gate's weight is moved by the motors. The other 85% is supported by a floating compartment inside the gate. Essentially, each gate is a ship. "You can't mess with Archimedes' principle," Marotta says with a smile. And because Lake Gatun also supplies drinking water to Panama's largest cities, the engineers built water-saving basins that recycle 60% of the water in each chamber. Overall, the new locks use 7% less water than the old ones. Every container ship passing through pays between $500,000 and $1 million. 90% of global trade is seaborne. The canal is the economic heart of Panama. "Was this a childhood dream?" someone asks Marotta. "This is a dream job for any engineer," she answers. "A project like this doesn't get built every day. The locks, the gates, everything. Every single day there was something to resolve. That's the beauty." The biggest ships passing through the new locks are over 1,200 feet long. You could lay the Eiffel Tower on its side inside a single chamber and still have room left over. Every container ship that transits the canal pays a colossal toll, between $500,000 and $1 million per crossing. And the canal handles dozens of crossings per day. The new locks were completed in 2016, almost exactly 102 years after the original canal opened. And one of the most striking things about the whole history of Panama, from de Lesseps' catastrophe through the American triumph to Marotta's modern expansion, is that each generation faced its own version of the scale trap. De Lesseps tried to apply desert methods to a jungle.
The Americans had to invent a lock system that dwarfed anything built before. And Marotta's team had to engineer gates that weighed 4,000 tons, but moved with the elegance of a revolving door, using Archimedes' buoyancy to do most of the heavy lifting. Each time, the proven solution from the previous era had to be reinvented. Each time, the engineers who succeeded were the ones who understood that bigger did not mean the same. The lesson of Panama is one of the harshest in the history of engineering, and the author Bent Fluevbjerg, in his book How Big Things Get Done, articulates it precisely. Past success is the worst teacher for future megaprojects. Success creates the illusion that you understand the task, but at a new scale, in a new geography, with new variables, the task transforms. The skills that brought you glory can turn out to be worthless. The diseases that did not exist in the desert are waiting in the jungle.
The rock that held firm in the isthmus crumbles in the mountains. De Lesseps was not a fool. He was brilliant. But his brilliance was calibrated for the Suez. Panama required an entirely different kind of brilliance, one that began with humility, with the recognition that past experience might be irrelevant. Canals reshaped the map of the world. But water is not only an obstacle to be rerouted, it is also energy, tremendous, relentless energy. And the next chapter of our story is about what happens when you take a small turbine designed for a textile mill in Massachusetts and scale it up to a 450-ton monster inside the largest dam on the planet. In 1834, a young British engineer named James B. Francis arrived in a bustling textile town called Lowell, Massachusetts. Lowell was one of the first planned industrial cities in America, a network of canals feeding water from the Merrimack River into dozens of cotton mills. The complex was producing roughly 52,000 feet of cloth every single day. But the mills were reaching a limit. The problem was power. The factories were driven by simple water wheels, large wooden paddles that turned as water fell into their buckets. Straightforward, reliable, and spectacularly inefficient. The wheels captured only a fraction of the energy available in the canal system. As demand for textiles grew, the mills needed more power from the same water supply. Francis was brought in to figure out how to squeeze every last drop of energy from the system. What he invented, deep underground beneath the canal complex, changed the world. The original device is still there, buried about 15 feet below ground level. It is the first Francis turbine. And this is where the hydroelectric revolution began. What Francis did was take the concept of a water wheel and reimagine it completely.
He turned the wheel on its side, enclosed it in a casing so that water contacted the entire working surface simultaneously, and added guide vanes, curved blades that directed the incoming water at the optimal angle onto the turbine's runner blades. Water entered through the guides, struck the blades, transferred its energy, and exited downward through the center. Nearly 90% of the water's kinetic energy was converted into rotational motion, an astonishing efficiency that no water wheel had ever approached. The design was so effective that the Francis turbine remains the most widely used type of hydroelectric turbine in the world today, almost 200 years later. And in its essential form, it has barely changed. The proportions have been refined, the materials upgraded from iron to steel to specialized alloys. The manufacturing precision increased by orders of magnitude. But the fundamental geometry, the enclosed casing, the guide vanes, the radial inflow runner, is still recognizably the machine that James Francis built in a textile town in Massachusetts. This is what makes the scaling of the Francis turbine so instructive. The principle works perfectly at every size. A small Francis turbine in a creek can power a single house. A medium one in a river can power a town. And a giant one in a dam can power a province. The physics does not change, but the engineering changes completely. At each new scale, entirely new problems appear. Problems of weight, of vibration, of material stress, of installation logistics, that the smaller version simply did not have. But generating electricity is only half the problem. You also have to deliver it to the people who need it. And this is where another genius enters the story. A man who was dismissed as a crackpot for much of his life. Nikola Tesla. At the end of the 19th century, engineers at Niagara Falls faced a tantalizing puzzle. The waterfall was one of the most powerful natural features on Earth. 150,000 gallons per second, plunging nearly 170 feet. The energy was right there, roaring and thundering, visible from miles away. Building a power plant beside the falls was not the hard part. The hard part was getting the electricity from Niagara to the cities that needed it: Buffalo, New York, and eventually much farther.
The problem is that electricity loses energy as it travels through wires. The longer the wire, the more energy is wasted as heat. In the 1890s, with the technology available, electricity could only be transmitted a few miles before the losses became unacceptable. Tesla solved this with one of the most important inventions in electrical history, the high-efficiency alternating current transformer.
Professor Andrew Smith finds the building where the breakthrough happened, the Adams Power Plant Transformer House at Niagara Falls. It might look like an old warehouse, he says, but this is actually a very special place. This is where, in 1895, the world's first large-scale hydroelectric plant went into action. And the man behind it was an engineering genius, Nikola Tesla. Smith demonstrates the principle with toy cars on two parallel tracks. Both cars received the same voltage, 6.8 volts. They start at the same moment and finish in a dead heat. Now, one track is connected through a step-up transformer. Same start, and the car on the transformer track pulls away decisively. A step-up transformer works like this. Electric current flows through a primary coil, creating an alternating magnetic field. A secondary coil with more wire windings sits nearby. The magnetic field induces a current in the secondary coil, and because of the additional windings, the output voltage is higher. Higher voltage means the electricity can travel much farther through the wires before the losses become significant. At the receiving end, a step-down transformer reduces the voltage back to a usable level. Instead of pushing toy cars down a track, Tesla's transformers at Niagara allowed engineers to fire electricity across enormous distances, from the thundering falls to the factories and homes of Buffalo, 20 miles away, with acceptable losses. Before Tesla, electricity was a local phenomenon. After Tesla, it became a networked resource that could be generated in one place and consumed in another, hundreds of miles away. That single innovation, high-voltage alternating current transmission, is the foundation of every electrical grid on Earth today. Every time you flip a light switch, you are using a system that traces its lineage directly back to this unassuming building beside Niagara Falls. Tesla, who for much of his life was dismissed as an eccentric dreamer, had literally electrified the modern world. Smith says it plainly. It was one of the most powerful engineering breakthroughs ever made in this historic building, now considered the birthplace of modern hydroelectric power. At the Three Gorges Dam, the ideas of Francis and Tesla have been scaled up to a level that neither man could have imagined. And to appreciate the scale of the transformation, it helps to hold both images in your mind at once. Francis's original turbine, sitting quietly 15 feet underground, beneath a Massachusetts textile canal, powering a few dozen looms. And the machines that now sit inside the Three Gorges powerhouse. 32 of the largest Francis turbines ever built. Each one weighs 450 tons, roughly the weight of a fully loaded Boeing 747. The runner alone, the spinning component at the heart of each turbine, is over 30 feet in diameter. At Francis's original scale, you could bolt a turbine to a wooden frame in an afternoon. At this scale, the crane needed to install a single turbine was so enormous that it had to be designed into the structure of the powerhouse before construction even began. The building was literally engineered around the crane. If the crane had been an afterthought, the powerhouse walls and roof would have had to be demolished and rebuilt to accommodate it. That is what scaling up means. The secondary systems, the cranes, the cooling, the logistics,
become primary engineering challenges in their own right. 2 turbine halls, each stretching the length of 6 football fields, house 16 turbines apiece.
Walking through them feels less like being inside a building and more like being inside a cathedral that hums. Engineer Jan Akinola stands inside one of the halls and asks the audience to be quiet for a moment. Just listen. This is the sound of huge quantities of water surging at speeds up to 80 miles per hour, spinning 32 of the biggest Francis turbines ever built. The sound is a deep, continuous roar, felt as much as heard, a vibration that travels through the concrete floor and up through your bones. Water enters through a series of giant intake structures at the upstream face of the dam. It then drops roughly 260 feet through massive steel penstocks, pipes large enough to drive a truck through, arriving at the turbines with a flow rate of up to 33,500 cubic feet per second. To put that in perspective, the flow through a single turbine at 3 Gorges is greater than the entire flow of many medium-sized rivers. That torrent spins each 450-ton runner at 75 revolutions per minute, and the rotation drives a generator mounted directly above, a machine that looks, from below, like a flying saucer, slowly turning. And above those generators sits the main transformer, a direct descendant of Tesla's Niagara invention. It steps up the voltage from 20 kilovolts to 500 kilovolts, a 25-fold increase, for transmission over 600 miles to Shanghai and beyond. Without this step-up, the electricity would lose most of its energy to heat before it traveled even 50 miles. Tesla's insight, that high voltage and low current travel far more efficiently than low voltage and high current, is the invisible infrastructure that makes the entire system work.
The dam generates almost 100 terawatt-hours of electricity every year, powering 9 provinces and 2 cities, including Shanghai, one of the largest metropolises on Earth. To put 100 terawatt-hours in perspective, it is roughly equivalent to the annual electricity consumption of a medium-sized European country. A single dam on a single river, producing the energy output of an entire nation. That is the scale of 3 Gorges, and every watt of it flows through descendants of the transformer that Tesla built beside Niagara Falls in 1895. But Chinese engineers did not stop at dams. Their ambition extended into the open sea, building bridges and tunnels on a scale that tested every limit of modern engineering. The Hong Kong-Zhuhai-Macau Bridge stretches across a 22-mile-wide expanse of the South China Sea. 550,000 tons of steel, 2.3 million tons of cement, 9 years of construction. It is the longest sea-crossing bridge ever built. But the most extraordinary part of the crossing is not above the water, it is below it. About 4 miles of the route passes through an immersed tube tunnel, a tunnel assembled from prefabricated sections sunk to the seabed. Why a tunnel instead of a bridge? Because directly above this stretch of water, airplanes approach Hong Kong International Airport on their landing path. Bridge pylons would be a hazard to aviation, and the waterway beneath serves major international shipping lanes. Bridge supports would obstruct navigation. Going underwater was the only option. 33 colossal tube sections were fabricated in a purpose-built factory on a nearby island. Each section was about 590 feet long and weighed 74,000 tons, comparable in scale to a medium-sized aircraft carrier. Once completed, each section was sealed at both ends to make it watertight, floated out to the construction site by tugboat, and then, carefully, painstakingly, lowered to the seabed. using ballast tanks. The joining process was the most nerve-wracking part. Each section had to align with its neighbour to a tolerance of just 3 millimeters, about 1/8 of an inch. On the seabed, in strong currents, with 74,000 tons of concrete and steel swaying gently on the end of a cable. One section too far to the left, one gust of current at the wrong moment, and months of work could be destroyed. International media called the process a subsea kiss of perfection. The engineers probably used less poetic language at the time. And then, even more audacious, came the Shenzhen-Zhongshan link, another immersed tube tunnel about 4¼ miles long, but this time with 8 lanes of traffic in each direction. When Dutch immersed tube specialists, the world leaders in this technology, were consulted, they declared an 8-lane bidirectional configuration impossible. The hydrodynamic pressures would be too great. The forces acting on such a wide tube at such depths could not be managed with conventional construction. The Chinese engineering team spent 3 years developing a solution, and when they presented it, the Dutch engineers who had said it was impossible acknowledged that the approach was sound. The solution was not a single innovation, but a system of innovations, each one addressing a different aspect of the scaling problem. Each additional lane increases the hydrostatic pressure on the tunnel structure by roughly 27%, about 20,000 tons per lane. That is like carrying the weight of 15,000 cars on your back. The engineers developed a steel-concrete sandwich composite structure, a steel shell filled with concrete, that delivered a 400% increase in flexural rigidity compared to traditional reinforced concrete. Robotic welding arms achieved seam alignment accuracy of 0.02 of a millimeter, about 1/1000th of an inch, roughly 1/3 the thickness of a human hair. Intelligent concrete pouring robots compressed a process that traditionally took 90 days into just 28. The concrete itself was a special self-compacting formulation that, in the words of the engineers, flows like melted dark chocolate, filling every cavity with nanometer precision. The American Society of Civil Engineers incorporated this steel-concrete sandwich technology into their latest design standards. What began as a response to a challenge that the world's leading experts called impossible became a new benchmark for the entire profession. And here is the part worth sitting with for a moment. Every one of these innovations, the composite structure, the robotic welding, the self-compacting concrete, was developed not because someone had a clever idea in a laboratory, but because the scale of the project demanded it. At a smaller scale, conventional reinforced concrete would have been fine. Conventional human welders would have been accurate enough. Conventional concrete, poured by hand, would have filled the forms adequately. It was only when the dimensions crossed a certain threshold, when the tunnel became wide enough for 16 lanes of traffic, when the sections became heavy enough to rival warships, when the tolerances tightened to fractions of a millimeter, that these innovations became necessary. The scale did not just require more engineering. It required different engineering, engineering that had not existed before the project demanded it. And all of it. Every tunnel section, every welded seam, every cubic yard of self-compacting concrete traces its ancestry back to the invention that John Smeaton made on a rock in the English Channel 250 years ago. Concrete that sets underwater. Only now, it is setting on the seabed, 140 feet down, inside sections the size of aircraft carriers. On Earth, engineers battle gravity, water, and wind. But what happens when the scale of the challenge leaves the planet entirely?
when you need to sustain human life in a place where there is no air, no pressure, and no warmth. And when the capsule carrying those humans has to survive not just one environment, but the transition between several, each one lethal in its own way. In 1930, a Swiss physicist named Auguste Piccard proposed an idea that most of his colleagues considered suicidal.
He wanted to fly into the stratosphere, more than 49,000 feet above the Earth, to study cosmic rays. The problem was straightforward and terrifying. At that altitude, the atmosphere is so thin that a human being cannot breathe. The pressure is so low that the fluids in your body begin to boil. The temperature is far below zero. Dr. Andrew Steele, a physicist, demonstrates what happens to the human body at extreme altitude using a marshmallow and a vacuum pump. He places the marshmallow inside a glass jar and begins extracting the air. As we pump out the air and reduce the pressure, the marshmallows start to expand. That is because they have little air pockets inside them, and when the pressure outside drops, those pockets get bigger. He watches the marshmallow swell to twice its size. If that were me, going up higher and higher, the gas pockets inside my body would start expanding, and at very low pressure, the liquids on the surface of my body would actually start to boil. Poor little guy. Piccard understood that if he wanted to survive the stratosphere, he would have to take the Earth's atmosphere with him. He conceived the first pressurized gondola in history, a sealed capsule that could maintain normal air pressure inside while the outside pressure dropped to almost nothing. To make the capsule absolutely airtight, he turned to an unexpected source of expertise, a beer barrel manufacturer. The capsule was made of aluminum, just a few centimeters thick, a little over 7 feet in diameter. Air recirculation was adapted from submarine technology. Liquid oxygen evaporated from a container to provide breathable air, and carbon dioxide was scrubbed by a reaction with soda lime. In 1931, an enormous hydrogen balloon lifted Piccard and his assistant above 49,000 feet. The ascent took hours. The temperature outside the gondola dropped to 40 below zero. The pressure fell to a fraction of sea-level atmosphere. Inside the aluminum capsule, barely large enough for 2 men and their instruments, the air remained breathable, the pressure remained survivable, and the temperature remained tolerable. They became the first human beings to reach the stratosphere. Through a tiny porthole, they glimpsed what no one had ever seen with the naked eye: the curvature of the Earth against the blackness of space. It was a small capsule, a short flight, and a modest altitude by today's standards. But it established the fundamental principle that would make all future high-altitude and space travel possible. You can take your environment with you. You are not limited to the places where your body can survive naturally. You can build a bubble of survivable atmosphere and carry it anywhere, as long as you understand the engineering of containment, life support, and pressure management. Piccard predicted that one day we would all fly high in the atmosphere, above the bad weather, where air resistance is lower and travel is faster. Without his pioneering experiments, neither commercial aviation nor spaceflight would have been possible. But Piccard's gondola was 7 feet across, 2 passengers, 10 hours of life support. Now scale that up. What if you need to keep 135 people alive for months at a time, 240 feet below the surface of the ocean, in total darkness, with no way to resupply? The Virginia-class submarine is one of the most complex engineering objects ever built. About 377 feet long, around 1 million individual components, 10 million man-hours to construct, and the key to its ability to stay submerged for months without surfacing lies in a single innovation: a nuclear reactor.
The story of nuclear submarines begins with one extraordinarily stubborn man, Captain Hyman Rickover of the United States Navy. The problem with submarines had always been simple. Most power sources require air. Diesel engines need oxygen to burn fuel. Batteries run out after about 48 hours. Every submarine in the world was forced to surface regularly, exposing itself to detection and attack. Rickover saw nuclear power as the solution. A reactor could generate steam for propulsion without consuming any oxygen at all. But there was a catch. Existing nuclear reactors were the size of buildings. How do you shrink one to fit inside a submarine hull? Rickover spent years developing the first compact pressurized water reactor, a design where the nuclear core heated a closed loop of water under tremendous pressure. This superheated water, in turn, boiled water in a secondary loop, producing steam to drive a turbine. Electricity, without air, without surfacing, without limits. In 1954, Rickover watched the launch of the USS Nautilus, the world's first nuclear-powered submarine. It traveled 1,300 miles in less than 90 hours, fully submerged. To appreciate what this meant, consider the previous state of the art. Conventional submarines could stay underwater for a maximum of 48 hours before their batteries died, and they were forced to surface, exposing themselves to detection and attack. The Nautilus shattered that barrier so completely that it might as well have belonged to a different century. The submarine was no longer a vessel that occasionally dove beneath the waves. It became a vessel that lived there. Rickover was not an easy man to work with. He was legendarily demanding, abrasive, and uncompromising. He personally interviewed every officer who served on his nuclear submarines, and his interview technique was infamous. He would do anything to unsettle the candidate, including sawing the front legs of the interview chair so it tilted forward. But his standards were the reason his reactors never failed. In the entire history of the US nuclear submarine program, more than 6,000 reactor years of operation, there has never been a reactor accident. That safety record is, in large part, Rickover's legacy. The Virginia-class submarines, commissioned from the early 2000s onward, represent the current peak of this technology. Their reactor is designed for the entire operational life of the ship, 33 years, without ever needing to be refueled. Nearly 1 million miles of underwater travel on a single core. The only factor that limits how long a Virginia-class submarine can stay submerged is not fuel, not power, not oxygen. It is the amount of food on board.
But how do you provide breathable air for 135 sailors over months of submersion? The answer reaches back to the year 1800, when an English chemist named William Nicholson became one of the first people to experiment with the newly invented electric battery. He submerged 2 electrodes in water and passed a current between them. On the negative electrode, hydrogen gas appeared. On the positive electrode, oxygen. Electrolysis. The splitting of water into its component gases using electricity. Rees-Morgan demonstrates the same experiment. 2 test tubes inverted over electrodes in a beaker of water. Current on, and bubbles begin rising into the tubes, displacing the water. He takes the oxygen tube and holds a glowing splint near its mouth. The splint bursts into bright flame. So we've produced, in a matter of seconds, enough oxygen to fill this test tube. In a submarine, this process is scaled up to provide enough oxygen for the entire crew. On the Virginia class, an advanced low-pressure electrolyzer produces over 200 cubic feet of oxygen per hour. Carbon dioxide, the byproduct of breathing, is removed by an amine-based scrubbing system. The atmosphere inside the submarine is maintained at roughly 21% oxygen, matching the air at the surface. Submarine crews breathe manufactured air for months on end, and most of them say they cannot tell the difference. And in case of emergency, if the submarine suffers a catastrophic failure and the crew needs to escape from a pressurized hull hundreds of feet underwater, there is the SEIE suit, the Submarine Escape Immersion Equipment. It is a one-piece hooded suit with an integrated life raft. 75 pounds of positive buoyancy. Once the submariner enters the escape trunk, the chamber floods, pressure equalizes with the sea, the outer hatch opens, and the suit, rocketing upward at 625 feet per minute, about 7 miles per hour, carries the sailor to the surface. It has been tested to depths of 600 feet of seawater. There is one absolute unbreakable rule during this ascent. Never, under any circumstances, hold your breath. Because a submariner breathes compressed air at depth, as they rise and the water pressure drops, that air expands inside their lungs. Hold your breath, and the expanding air can rupture the alveoli. The instruction is clear, simple, and non-negotiable. Breathe out, all the way up. Now let us make one more jump in scale. From a submarine beneath the ocean to a spacecraft headed for Mars. The Orion Crew Module is the most advanced exploration vehicle NASA has ever built. Its destination? Mars. Over 62 million miles from Earth at its closest approach. 9 months of travel, one way. The capsule is about 16.5 feet in diameter, 40% larger than the Apollo command module that carried astronauts to the moon. Some people will compare Orion to Apollo, and in its basic shape, a cone with a heat shield, the resemblance is clear. But in every other respect, they are generations apart. The hull is made from a lithium-aluminum alloy, lighter and stronger than conventional aluminum. Each of the capsule's 7 structural panels is machined on a single milling machine for 6 months. During that process, up to 90% of the original metal is cut away, leaving behind a thin, precisely shaped shell. "Mass is gold," says production manager Mark Moscovich. "Every gram I can shave off the structure is a gram of astronaut, a gram of something that flies to space." Traditional welding deforms metal as it cools, so NASA engineers use a technique called friction stir welding. A rotating tool presses against the metal surfaces, heating them to a plastic state through friction, and then stirring the softened metal together. The material never actually melts. The resulting joint is as strong as the surrounding metal, with none of the warping that conventional welding would produce. Navigation is another story of scale. Close to Earth, radio communication with mission control provides constant guidance. But on the way to Mars, radio signals take up to 24 minutes to travel each way. If something goes wrong, the crew cannot wait 48 minutes for instructions. They need autonomous navigation. The Orion is equipped with an optical navigation camera that measures the apparent diameter of the Moon and the angles between the Moon and background stars.
By comparing these measurements with onboard star charts, the computer can calculate the spacecraft's position without any input from Earth. And as a backup, in case the intense radiation environment of deep space damages the onboard computers, the crew will carry a sextant, the very same instrument that John Bird designed in 1757 for maritime navigation. Dr. Andrew Steele tests a replica at sea, measuring the angle of the sun above the horizon and performing the calculations by hand. His result? Latitude about 49 degrees and 55 minutes north, longitude 5 degrees and 27 minutes west. He checks against a GPS receiver. The sextant reading is accurate to within about 1,600 feet. For a piece of equipment designed in the 1700s, Steele says, that's incredible. Think about that for a moment. A crew of astronauts traveling through interplanetary space in the most advanced vehicle ever constructed. carrying a backup navigation instrument that predates the French Revolution. An instrument made of mirrors and graduated arcs, designed for wooden sailing ships, now serving as the last resort guidance system for a spacecraft headed to another planet. On the first Orion flights beyond the Moon, astronauts will have a sextant in the cockpit. If radiation from the Martian environment damages the onboard computers, a real and serious concern over a 9-month journey, they will find their way home by the stars, using a technique that is 270 years old. And the reason it will work is that the stars have not moved. The math has not changed. The sextant remains, after all these centuries, one of the most reliable instruments ever designed. And then there is the rocket that will carry Orion to orbit.
The Space Launch System, SLS, is the most powerful rocket ever built. 8.4 million pounds of thrust, taller than the Statue of Liberty, longer than a football field. Its mission? To lift 70 metric tons of payload into orbit, with a future version capable of 130. 4 RS-25 engines, veteran designs from the Space Shuttle era, provide the main propulsion. Engineer Steve Wirtz calls them the Mona Lisa of mechanical engineering. 2 solid rocket boosters, the largest ever built, provide the initial punch off the launch pad, and the lineage of this machine reaches back almost exactly a century, to a man who was ridiculed for believing that rockets could work in the vacuum of space. Robert H. Goddard, an American engineer, launched his first liquid-fueled rocket in 1926. It was called Nell. It flew 41 feet in just 2 seconds before crashing back to Earth.
A tiny, sputtering flight, but it proved a principle that the scientific establishment of the time considered absurd. The New York Times wrote that Goddard did not understand basic physics, that a rocket could not work in space because there was no air to push against. Goddard understood Newton's third law better than his critics. For every action, there is an equal and opposite reaction. The rocket pushes exhaust downward. The reaction pushes the rocket upward. No air required. Over the following years, Goddard launched 34 liquid-fueled rockets, reaching altitudes of about 8,200 feet and speeds approaching 745 miles per hour. Each launch taught him something new, about fuel mixtures, about gyroscopic stabilization, about the dozens of ways a rocket can fail. He worked in relative obscurity in Roswell, New Mexico, funded partly by the Smithsonian Institution and partly by the Guggenheim family.
He died in 1945, never seeing his work vindicated. In 1969, the day after Apollo 11 launched for the Moon on a rocket that owed everything to Goddard's pioneering work, the New York Times published a quiet correction to their 1920 editorial. "It is now definitely established," the paper noted, "that a rocket can function in a vacuum as well as in an atmosphere. The Times regrets the error. 49 years late. The SLS that will carry Orion to orbit is taller than the Statue of Liberty and longer than a football field. Its 4 RS-25 engines, each one an engineering masterpiece refined over decades of space shuttle flights, burn liquid hydrogen and liquid oxygen at temperatures and pressures that would destroy most metals in seconds. The 2 solid rocket boosters strapped to its sides are the largest ever constructed.
Together, they produce 8.4 million pounds of thrust at liftoff, enough force to accelerate a 70 metric ton payload to orbital velocity. And that payload, the Orion capsule and its service module, will eventually carry 4 astronauts to Mars. By 2035, if the current timeline holds. The distance from Goddard's 41-foot flight to Orion's 62-million-mile journey is perhaps the most staggering example of scaling in this entire story. From a marshmallow in a vacuum jar to a capsule machined from lithium aluminum for 6 months. From a beer barrel manufacturer's pressurized gondola to a nuclear reactor that runs for 33 years without refueling. From a knotted rope and a sextant to optical navigation cameras locked onto distant stars. Every component in this chapter survived its own scale trap. Every one was reinvented, sometimes multiple times, for a new order of magnitude. And every one succeeded, because the engineers behind it understood that scaling up meant not just making things bigger, but making them different. All of the projects in this story succeeded, but what happens when that understanding is missing? When someone looks at a proven small design and says with complete confidence, "Let's just make it bigger." When the financial advisor replaces the engineer and the architect ignores the rain. This chapter is about failures. About the moments when engineers, architects, or simply overconfident people decided that bigger meant the same thing, only larger. And reality answered. January 15, 1919, Boston, Massachusetts. A company called Purity Distilling processed molasses, a thick, dark, extraordinarily viscous liquid, a byproduct of sugar refining. Their storage tank stood about 50 feet tall and held over 2 million gallons. And here is the critical detail. The construction of that tank was overseen by a man named Arthur P. Gell. Gell was a financial advisor. He had no engineering training, no structural expertise, no understanding of the forces acting on a 50-foot cylindrical vessel filled with 2 million gallons of dense liquid. But he was cheaper than a qualified engineer. When cracks appeared on the tank, they were patched. When more cracks appeared and molasses began visibly leaking through the seams, the company made what it considered a brilliant decision. They painted the tank brown. The logic was simple. If the leaks are not visible, the problem does not exist. On that unseasonably warm January afternoon, temperatures had risen sharply from below freezing the day before, causing the cold molasses inside the tank to expand against the already weakened walls. The tank ruptured. The failure was sudden, total, and catastrophic. Over 2 million gallons of molasses burst outward. A wave, reportedly 55 feet tall according to eyewitnesses, surged through the narrow streets of Boston's North End at 35 miles per hour. Molasses is about 40% denser than water. Once you are caught in it, you cannot swim, you cannot push through, you cannot escape. 150 people were injured. More than 300 volunteers spent weeks cleaning the streets. The company tried to blame the disaster on anarchists. A court ruled otherwise and ordered them to pay $300,000 in damages, about $5.1 million in today's money. The lesson? A 50-foot industrial tank holding millions of gallons of dense liquid is not a household project. It requires industrial-grade engineering. When the person overseeing its construction is a financial advisor who has never studied the behavior of pressurized fluids, the outcome is predictable. Just not to the person who caused it. 2003, Los Angeles. The Walt Disney Company commissioned the celebrated architect Frank Gehry to design a new concert hall. The result was a futuristic building clad in 12,500 curvy stainless steel panels. A dazzling, undulating surface that caught the California sun from every angle. The problems emerged immediately after opening. The panels were so reflective that looking at the building during the day was like staring directly at the sun. Worse, the hall sat beside a major freeway, and the reflected glare was temporarily blinding multiple drivers. And worse still, the curved panels did not merely reflect light, they focused heat. The sidewalk temperature around the building reached 140 degrees Fahrenheit.
hot enough to cause serious burns. Disney quickly realized they had installed a permanent lawsuit-generating machine in the middle of Los Angeles.
A beautiful, award-winning, architecturally celebrated lawsuit-generating machine, but a lawsuit-generating machine nonetheless. Every single one of those 12,500 panels was sanded down to reduce their reflectivity. The building became less dazzling than Geary had intended, but considerably safer for everyone around it. What makes the Disney Concert Hall interesting from a scale trap perspective is that Geary's curved panels work beautifully on smaller buildings. At a modest size, the reflected light is a pleasant shimmer, the focused heat is negligible. It is only when you scale the concept up to 12,500 panels on a massive structure beside a busy freeway in one of the sunniest cities in America that the shimmer becomes a death ray, and the negligible heat becomes a sidewalk that can fry an egg. Venice, 2008. The celebrated Spanish architect Santiago Calatrava designed the fourth bridge across the Grand Canal, the Ponte della Costituzione, or Constitution Bridge. It was elegant, curving, and transparent. To achieve the effect of transparency, Calatrava chose glass as the primary surface material. The problem is embarrassingly simple. Venice receives about 32 inches of rain per year, fairly evenly distributed across the months. Glass is a notoriously slippery material when wet. In winter, rain on cold glass freezes, turning the bridge into an ice slide. There was no ramp for wheelchairs or strollers, only steps. The bridge quickly became infamous among locals and tourists alike as a site of constant falls and injuries. And here is the most telling part. Calatrava had made this exact mistake before. His Zubizurri Bridge in Bilbao, also made primarily of glass, had the same problem: slippery in rain. Same architect, same material, same failure. Twice. Eventually, the city of Venice covered the glass surface with a series of stone panels, destroying the bridge's intended aesthetic, but making it possible to walk across without risking a broken hip. The cost of the bridge, originally estimated at about €7 million, eventually exceeded 11 million. And the most galling aspect of the whole affair was not the cost, not the slipperiness, and not the lack of wheelchair access. It was that the architect had already proven in Bilbao that glass bridges are slippery in rain, and went ahead and built another one in a city famous for its rain and flooding. The scale trap here was not about physical size. It was about the scaling of consequences. A slippery footbridge in Bilbao is an inconvenience. A slippery bridge across the Grand Canal in Venice, used by thousands of tourists and elderly residents daily, is a public safety crisis. And then there is a story that sounds like a joke, but is entirely real. In 2006, a user of the internet forum Something Awful, posting under the name Grover, announced that he would build his own house based on his own design, drafted in the drawing program MS Paint. He had no architectural training, no engineering qualifications, no construction experience. The result? A house with 7 windows in 4 different styles on a single facade. 8 electrical outlets lined up a foot apart from one another on the kitchen wall. A window positioned so perfectly that if you fell down the stairs, you would also crash through the window into the swamp below. And yes, the house was built in a location called the Great Dismal Swamp, a real swamp in Virginia. Load-bearing walls were constructed from drywall, a notoriously flimsy material designed for interior partitions, not structural support.
When the house failed its safety inspection, Grover found a creative solution. He obtained a qualification as a health and safety inspector, giving himself the authority to certify his own house as safe. There is something almost admirable about the determination, if not the judgment. Let us look at one more failure, and then one more lesson, because they come from different ends of the spectrum, and together they complete the picture. The failure is thermal expansion in railroad tracks, a problem so simple it seems absurd, and yet it has caused derailments and disruptions across the world. Metal expands when heated and contracts when cooled. Over a few feet of track, the expansion is negligible, maybe a fraction of an inch. But over miles of continuous welded rail, a hot summer day can add enough length to buckle the track sideways. The rails twist and wave like spaghetti, turning a perfectly functional railway into something resembling a roller coaster.
The solution is a process called stressing. Before installation, rails are heated or stretched to an intermediate length so they have room to expand and contract within a safe range. Tracks that skip the stressing process work perfectly well in moderate temperatures, but when a heat wave hits and the scale of thermal expansion exceeds the margins, the rails deform and they do not snap back. The images are almost comical. Almost. Until you remember that freight trains weighing thousands of tons are supposed to be running on them. Henry Petrosky, the author of To Engineer is Human, described the core principle of engineering as the anticipation of failure. A good engineer spends most of their time imagining every possible way a structure could fail and designing protections against each one. The margin of safety that medieval cathedral builders used, making columns 20 to 30 times stronger than necessary, was an intuitive version of this principle.
They could not calculate the forces precisely, so they compensated with massive over-engineering. And it worked, spectacularly, for centuries, until someone at Beauvais decided that the margin could be reduced. The principle applies at every scale. A child building a tower of wooden blocks learns it instinctively. The taller the tower, the more careful you have to be. The blocks at the bottom carry all the weight. The slightest wobble at the top brings everything down. What the child learns through play, the engineer learns through calculation, and sometimes through disaster. When that anticipation of failure is absent, when a tank is designed by a financial advisor who has never studied fluid dynamics, when a building is designed without modeling how its surfaces interact with sunlight, when a bridge is designed by an architect who has already proven that his material is unsuitable for wet climates, and when a house is designed in MS Paint by someone whose primary qualification is enthusiasm, scale bites without warning. The consequences are proportional to the ambition. A poorly built garden shed collapses and you lose some tools. A poorly built 50-foot industrial tank collapses and a neighborhood is buried in molasses. Bent Floofbjerg, in How Big Things Get Done, adds a complementary principle. Think slow, act fast. The best megaprojects in history, the Eiffel Tower, the Millau Viaduct, the modern Panama Canal locks, were projects where the majority of time and effort went into planning, modeling, and anticipating problems. The actual construction proceeded quickly and precisely, because every detail had been thought through in advance. The worst projects were the ones where construction began before the planners understood what they were dealing with. De Lesseps in Panama, the builders of Beauvais Cathedral, the owners of the Boston molasses tank. Every time, the same pattern. Confidence that past experience was sufficient for a new challenge. And every time, the new challenge turned out to be a different beast entirely. But not every encounter with scale ends in disaster. Sometimes, the lesson is caught just in time. The AT&T Stadium in Arlington, Texas, home of the Dallas Cowboys, is one of the largest enclosed structures in the world. Its retractable roof
spans more than 1,000 feet on two enormous steel arches. Those arches are the longest single-span arches ever used in a building. And when engineers first modelled the retractable roof's operating mechanism, they hit a problem. The steel panels of the roof had to climb from horizontal to a steep angle, and the mechanism for driving them needed to generate enormous force on a steep incline. The solution came from an unlikely source: the Mount Washington Cog Railway, built in 1869. The railway uses a rack and pinion system, a toothed gear meshing with a toothed rail, to climb the steepest slopes. Engineers adapted this Victorian-era mechanism for the stadium roof, using massive rack and pinion drives to push the 2,000-ton panels up the curvature of the arch. The mechanism was tested and retested before the stadium opened. No failure. But the engineers acknowledged publicly that scaling a railway mechanism to stadium roof size required months of additional engineering that nobody had anticipated at the start of the project.
That is the difference between the builders who succeed and the ones who fail. Both encounter the scale trap. Both discover problems that did not exist at the previous size. The ones who succeed expect that discovery. They budget time for it. They treat the unknown unknowns as a certainty, not a surprise. And that is the thread connecting every failure in this chapter. The molasses tank, the concert hall, the glass bridge, the MS paint house, the unstressed rails. In every case, someone assumed that a design that worked at one scale or in one set of conditions would work at another. The molasses tank was probably fine as a concept, at 1/10 of the size, supervised by an engineer. Gary's curved panels were probably fine on a smaller building, away from a freeway in a cloudier climate. Calatrava's glass was probably fine on a footbridge in a dry country where rain is rare. And railroad track works fine, until the temperature does something it has never done before, and the miles of continuous rail suddenly have nowhere to put their extra length. Every one of these failures is a small-scale version of the same lesson that Beauvais Cathedral, the Panama Canal, and the Three Gorges Dam taught on a grand scale. The rules do not change when you scale up, but new rules appear, rules that were invisible at the smaller size. And if you do not go looking for them, they will find you. Scale does not forgive overconfidence. And so we have traveled a long road tonight, from the stone pyramids of Giza, where a knotted rope was the only theory of construction, to the undersea tunnels of the South China Sea, where robotic welding arms work to an accuracy of 1/1000th of an inch. From a marshmallow swelling in a vacuum jar, to a spacecraft capsule machined from lithium aluminum over 6 months. From John Smeaton's lighthouse on a rock in the English Channel, to 450-ton turbines inside the largest dam on the planet. And at every single turn, the same lesson. Scale is not multiplication. Every order of magnitude brings new problems. Solutions that worked brilliantly for a small structure lose their meaning when that structure grows tenfold. Forces that were negligible become dominant. Materials that were strong enough become brittle. Assumptions that were safe become lethal. The builders of Beauvais knew how to construct a vault at 139 feet. At 159, the stone gave out. De Lesseps knew how to dig a canal through a desert. In a jungle, his knowledge proved worthless. James Francis built a turbine for a textile mill, and to scale it to 450 tons, engineers had to redesign the entire building around it.
Frank Crow's cold water pipes kept Hoover Dam from cracking. But at the Three Gorges, those same pipes were just the beginning of a solution that required an entire industrial cooling infrastructure. And the most dangerous words in engineering remain. Let's just do what we did before, only bigger. But there is another side to this story. Every timescale exposed a new problem. Someone found an answer. Frank Crowe invented cold water pipes. Gilbert Roberts flipped an aeroplane wing upside down. Roy Plunkett stumbled onto Teflon by accident. Auguste Piccard asked a beer barrel maker to build him a spaceship. And each of those answers became a stepping stone for the next generation of engineers, who scaled it further still, and ran into problems that the previous generation could not have imagined. An endless spiral. And that spiral is what drives all of human progress. Right now, as you lie here, somewhere on the other side of the world, an engineer is looking at a set of drawings and thinking, what if we made this 10 times larger? And then there is a long pause. Because a good engineer knows that behind that question lies not just an increase in size, but a transformation. New forces, new materials, new problems that do not yet have names. And that engineer is not sleeping. She is thinking, drawing, making mistakes, revising, making new mistakes, and eventually finding an answer that will allow the next generation to reach higher, farther, and deeper than anyone thought possible. This is what Bent Fluvier calls thinking slow and acting fast. The best projects in history, the ones that came in on time and on budget and still stand centuries later, were the ones where the majority of the effort went into understanding the problem before a single shovel hit the ground. The Eiffel Tower, the Millau Viaduct, the modern Panama locks.
In every case, the construction phase was almost anticlimactic. Fast, precise, uneventful, because the thinking had been done first. Every building around you, every bridge you have driven across, every plane you have flown in, is the result of this process. Thousands of years of trial and error, thousands of engineers, each one pushing the solution to a single ancient problem just a little further. How to build bigger than seems possible, without destroying what you build. It is quiet, stubborn, painstaking work. Almost invisible. You will never see a headline that reads, "Bridge does not collapse," or "Dam holds water successfully." The work of engineering is noticed only when it fails. When it succeeds, which is overwhelmingly most of the time, it simply disappears into the background of daily life, holding everything in place without complaint. And that, perhaps, is the most remarkable thing about it. The world stands, and nobody thinks about why.
So let that thought settle over you as you drift off. Somewhere, right now, concrete is curing. Steel is cooling. A cable is being tensioned to within a fraction of an inch. And someone is checking one more time that everything is in place. The phone on your nightstand, if it is there, contains transistors that are 7 nanometers wide. A human hair is roughly 80,000 nanometers. To manufacture those transistors, engineers had to solve problems of scale that did not exist when the first integrated circuits were built in the 1960s. Problems of quantum tunneling, of atomic-level contamination, of heat dissipation in spaces smaller than a virus. Every generation of chips required not just smaller components, but entirely new physics. That is the scale trap. And it is everywhere.
In every direction. Up, down, bigger, smaller, faster, slower. The moment you push past what has been done before, you enter territory where old rules apply, but new rules dominate. And the only way through is to recognize the transformation for what it is, and to engineer your way out. sleep well. The world will still be standing in the morning because someone, somewhere, stayed awake.